Hi, I'm Tim Pennington, and this is Seen and Solved by Hubbard-Hall. And on this episode, we're going to take a walk down memory lane and take a look back at all the shows that we've had in 2022 and revisit some of our favorite moments from Seen and Solved. I'm Tim Pennington, and you're listening to Seen and Solved, brought to you by Hubbard-Hall. Better results, less chemistry. And we're going to kick it off with Robin Deal, who we discussed metal removing for the industrial wastewater treatment systems. You know, the big challenge, I guess, with a lot of shops is removing it safely, and removing it efficiently. So let's talk about those three things. So what is used to remove the metals?
So when you remove metals, the most common process is a process called hydroxide precipitation, where you increase your pH with the sodium hydroxide, and then you introduce a flocculant or a polymer. Layman term, in wastewater, we call it snot because it's extremely slimy.
Ooh, wow. Okay.
And
that's actually a technical term?
That's a technical term in wastewater.
Who would have thought that?
And then you allow the solids to settle out, and your clear supernate goes out as your effluent. So that's the easiest process to do. Unfortunately, it's not always that easy with plating wastewater or some cleaning applications, because there's a thing called chelation and chelating agents that are introduced in the manufacturing side to assist those processes. So there's a very extensive list. There's numerous chelating agents out there in the world, but some of the strongest ones that we see in wastewater are citric acid, EDTA, pyrophosphate. Even though on a chemical engineering side or a chemical side, pyrophosphate is considered a sequestering agent, not a chelating agent. There's a difference between those two. But when it comes to wastewater, if you have pyrophosphate and it touches nickel, it will not release nickel.
Next, Joshua McLennan revealed how cleaning can be a very complex process. And maybe this is the problem. There's a lot of variables that people have when they're cleaning parts. A lot of things can go wrong. A lot of things can go right, but more often, if they're not paying attention, a lot of things can go wrong. So let's talk about the variables. What are some things that people need to have a good consideration of when they're actually in the cleaning process?
Well, there are several variables. I'll name them all. The concentration, time, temperature, agitation, the type of soil, and rinsing. And all of them play a different role in the cleaning process, depending on especially like if you're going to do silk cleaning versus spray cleaning. So for instance, like for concentration, I mean, that's the amount of cleaning you actually put in your bath to actually clean the part. And sometimes you can put too much cleaning, which will then actually can affect the part being clean. So actually knowing what concentration you really need, it's actually a big variable in this process. Also with time, sometimes it might take 2 minutes to clean your product. Sometimes it might take over 3 hours, just depending on that process. But you got to know, because if you over clean, sometimes you can have a bigger problem because it's too clean. Then it might cause like rusting or something. So just kind of knowing the time frame to clean that certain part.
Scott Papps dropped by to talk about today's supply chain issues. One thing that Hubbard-Hall has talked about, and I've actually seen it and explained to me, and I get it, is, even though you all are a chemical company, one of the things that you're trying to tell people is you may not need to use as much chemicals. So in a broad sense, explain what that means, because like I said, I've seen some good examples, but I'll let you talk about it. Of you may not need to use as much chemicals.
Correct. And it is a big shift from a corporate, viewpoint. Is, traditionally, we're trying to sell volume. That is, where we make our money, moving goods, whether we're blending them or doing them as the commodity distribution, moving them through, repackaging and supplying them. But it's realizing, we in trying to meet the needs of our customers, that approach is not the way to go long term. Many of the chemistries that we sell, we do it on the specialty side. A lot of our chemicals are for surface preparation cleaning. which isn't necessarily a value-added step. It's a necessary step. The give a clean part, get good surface to bond to get performance. But in its own, it doesn't value add. The end consumer isn't paying more for that step. So from the customer's perspective, they're always, that's the first place you're looking, trying to drive cost out of the business. So, we're looking at it, how to be a better partner. Then it's also a good steward for the environment. Putting stuff, you got to dispose of it when you're done with it down the drain. Well, we're committed to doing our best to help the environment. So to meet the customer needs, do the right things, is we're bringing technologies or even just auditing processes to find waste. Every process has waste. And that is something that, we have the knowledge, the experience to uncover and give alternatives to it.
Then Connor Calais dropped by to tell us about the paint stripping process. So finishing a coating industry, we're all talking about putting coatings on, getting it finished, but you are specializing in getting coatings off, right? I mean,
yes,
there is a need for that. Tell us why facilities, shops, why do they need to get rid of paint? Why do they need to strip parts?
Sure. So one of I'd say the primary cases we see that people have to remove paint or other similar organic coatings would be for the racks. I mean, as racks and different masking materials are run through a paint line with parts, they slowly accumulate a really large buildup of paint that has to be removed from some sort of mechanism, or it's just going to be rendered useless. Reclaiming those is both very cost effective because they need to not have to just buy new racks or maskings over and over again, but it's also an efficiency saver in the actual process, because if you don't have racks, you can't paint parts. If you can't mask the materials, you can't paint the parts. So having those readily available in a clean and effective manner is really important to maintaining the efficiency of all these different painting applications.
Larry Hensley came on to tell us all that we needed to know about corrosion. You talked about rust prevention, so let's talk about that. What are some ways to reduce the corrosion from occurring? I mean, we're talking, at the whether it was a facility that made the part or even a facility that's getting it ready to coat it. So what are some ways to reduce this corrosion, which, like you mentioned, has already started? What are some ways to kind of reduce it from getting worse?
Okay. We'll do it in stages. Here we call it classes of corrosion preventatives. We have temporary rust inhibitors, which are typically your water-based, amine-based rust preventatives that you apply to the surface of the part after manufacturing, after plating or phosphating. Your plating and paint customers, powder coating customers, they use a lot of in-process rust preventatives that are easily removed prior to powder coating, painting, or plating without contaminating the process. Those are water-based products. Typically, they last anywhere from 2 days to 2 weeks. Those are your typical short-term in-process products. Then you get into your next class of products, is what we call our soluble oils or emulsified oils. And it's where you mix oils with water, and you're going against everything, the mechanics of oil. Oil and water typically split. So you add emulsifiers to tie them together to make a longer term corrosion protection for, let's say 24 hours of salt spray protection to 72 hours of salt spray protection. That's pretty typical for a soluble oil. People would choose that because it's more or cheaper or more economical. Let's call it economical. You would be able to apply this to the part in a diluted form. You dilute it. 1 part rust preventative to 9 parts water, 10%, up to 20%. And you can reduce your cost that way. The problem is it's shorter bath life. Contamination causes the emulsion to split, and you have to replace the oil. So there are some drawbacks. But for somebody that needs an economical rust preventative, that's a good common use.
Next, Jeff Davis stopped by to talk about the evolution of solvents in a very comprehensive 2-part series. But why is it that these shops really need to take the cleaning process seriously, and really to know, more importantly, what can go wrong if they do not remove the soils from these parts?
Well, that's an excellent question, because historically, if you're a job shop or a captive shop, job shop being one that gets paid to clean and finish parts, or a captive shop, which is one process, potentially an automotive or an aerospace company, typically it's not a value added step. I mean, no job shop gets paid for cleaning a part. They get paid for the finish on the part. So they have to get whatever contaminants are on the parts off as judiciously and affordably as possible. So you always have that underlying message of what's the least expensive way for me to clean these parts. And that's what it's been like for the last 50 or 60 years. So that's why there's always been, you go up the value chain. So the chlorinated solvents, right now you typically have methylene chloride, which has really kind of been really in a lot of disfavor, if you will, in the United States. That's an excellent paint stripper, but has all sorts of issues related to parts per million exposure and potential carcinogens. You have trichloroethylene and perchloroethylene. Those three are really the workhorses, with tri and perc being the most available and the most commercially viable parts. And typically, historically anyway, have been most affordable on the per pound cleaned.
But there could be bans on use, production, or import of the chemical.
Even disposal of the chemical, or
There could be restrictions on equipment that you use, and or just monitoring requirements.
And since some of you may know, I have a checkered past. I have a background in biochemistry and clinical chemistry. Mm-hmm. One of my questions has been, when does an unreasonable risk become a reasonable risk? An unreasonable risk is kind of a non-quantified thing. Well, they're starting to say it. They've quantified unreasonable, and those levels are very, very low. They have what they call an ECHL, rhymes with freckle, and it stands for existing chemical exposure limit.
We welcome back Robin Deal once again, and she helped shed some light on how she deals with difficult metals. We're going to call this one meddling metals, the metals that seem to give most finishers the biggest problems. And I'm going to call out a few. Tell me if there's more. Chrome, which is on everybody's target. Nickel, zinc, copper. What else is out there that always seems to be causing problems?
Those are the four big ones. Occasionally we'll get a call for something like cadmium. The most exotic one that I ever received a call for was thallium.
And that's an element. I'm taking your word for that, correct?
It is one of the radioactive.
Well, when that comes up on Jeopardy, I am set. Connor Calais returned to us for a 3-part series on the differences between phosphates and pretreatments. Yeah, I guess the end result would be whether they're getting rejects, good adhesion, those type of things. They're going to know quickly if they're not doing it right.
Absolutely. And then on the other side, since this is a larger umbrella, sometimes you're not going to a paint booth, but you need this surface coating on a part because it needs to be not susceptible to corrosion in the field. So if you're doing sometimes or oftentimes with a zinc or a manganese coating, you need to make sure that you're getting a certain either coating weight or coating distribution to ensure that you have no voids basically on the surface of the part. And those voids are tend to be where you're going to have corrosion or rusting sort of stemming from. So one way we kind of quantify that was we'll do what we call coating weight analysis. So you basically take a part with a known surface area that you've already treated, get an analytical weight for that, thoroughly dry it before you do that. So that you're weighing just the bare component or steel in addition to the coating that's been applied to it. Then you use either chromic acid or a concentrated hydroxide, and you can strip that coating off, thoroughly clean and dry it again and reweigh it. And then that net difference of the weight divided by the surface area of the part that you've been analyzing, you can derive a coating weight. And that's very important metric for a lot of applications.
101 question. Talk about phosphates in general. Explain what those are and how finishers are using those.
So phosphates kind of fall under the class of a pre-treatment application. It's where you're going to take like a bare surface metal and you would apply this phosphate coating over the top of the metal in order to give it some sort of advantage with mechanical properties such as either paint adhesion or lubricity. Also can provide some corrosion protection to the part. Or some people just want to have more of a rougher finish on a stock material that these coatings can provide.
So like I said, we learned a lot about zinc and magnesium. So why would someone choose to use iron phosphates? What are some of the advantages that they would use that in their process?
Sure. So when we look at the phosphating as a whole, we talked earlier about how magnesium and zinc phosphate applications can give you a variety of mechanical benefits. But oftentimes what you really just need out of this coating is for it to be able to provide you with appropriate paint adhesion. Because if you're going to be coating a part, then painting over it shortly thereafter, you don't necessarily need some of those other properties that those more conventional methods provide. So when we look at iron phosphate in particular, what it allows us to do is to be able to get us that adhesion on the surface of the bare metal that we want in order for the paint to adhere properly and to be able to have those robust properties out in the field. But it does so in a much more similar method. So while you can spray some of the zinc phosphate chemistries, typically those zinc and magnesium processes tend to be done more of an application that uses immersion. Whereas with iron phosphates, you can easily combine those and utilize them in both an immersion process, but also a spray process. So they can be done very easily in a continuous line where you go from your pre-treatment and then they continue on a conveyor immediately into a paint booth. So they allow you to kind of maintain that process in a much more automated manner.
Thanks for listening to Seen and Solved, brought to you by Hubbard-Hall. I'm your host, Tim Pennington, wishing you happy holidays and a happy new year. And we can't wait to see what 2023 brings us. Seen and Solved is brought to you by Hubbard-Hall. Better results, less chemistry. For more podcasts, go to hubbardhall.com or wherever you get your podcasts.